Hello once again to all of you. I am Harshavinash Tanti and I am currently a research scholar at Department of Astronomy, Astrophysics and Space Engineering at IIT Indore, and I am your current course TA. So let's begin today's lecture. So today's lecture is about doing some computational examples on Python to understand few concepts more clearly. Okay, so as for today's overview, what we will go through will be what is 1D FFT, one dimensional FFT, okay, which you have learned in week 4, specifically lecture 2, and lecture 3 we will be covering. So what is 1D FFT, what is 2-dimensional FFT? See, you might have sir might have introduced some aperture distribution as well as few examples of that, but if you say you have an aperture or an area, so that is in 2 dimension, okay, and sometimes in 3 dimension also, there is Z also, but mostly we can assume it as a flat screen and take it a 2 dimension thing. So in that case, and also we studied that in, I think, lecture week 8 that week 7, that aperture and the signal obtained is in Fourier transform relationship, as well as the visibility and the intensity also. So here we will see how the what is 2D transformation, Fourier transformation, and how we can use how we can visualize it. Okay, now we will also see what is DFT and FFT. We will discuss it about a bit later, why DFT and FFT. And after that we will learn about something called correlation, as you might have also covered in this or the previous week, that if we want to go for interferometer technique, we have to correlate 2 signals. So how to correlate, that is also we will cover, and the additional topic is sampling, which is very important, and how it affects your data. And basically the thing we will discuss here is aliasing. Okay, so let's move to the review and a short review and introduction about it. So what we will have here is so we will cover what week 7 lecture 4. In week 7 lecture 4 we covered Python, how means a typical crash course is Python, and how we can utilize it as a computational tool. That was a bit hasty, but we will go through one by one each and every example, and I will explain in a step-by-step way manner what we are doing. Okay, so don't need to worry about it. Now also furthermore we will visualize what we are computing, means like by means of plotting and all those things. Then let's quickly cover the basics, means like how you can utilize Python online, which is also called Python notebook, that is IPYNB notebook. Okay, so what you have to do, you have to go to this link here. Okay, so this link you have to go, where when you go to this link, which is Google Colab, that will redirect you to your Google accounts login page. So there you have to put in your Google ID and password, and you will be ready to go. Okay, now let's before going to the Python scripting or visualizing our codes and everything, what we will do, we will quickly revise few concepts. Okay, so if you recall week 4 lecture 2, what we covered there, how the Fourier series converts into Fourier transform, and the general equation is given like this. Okay, but one thing I will say, and the inverse of this is this. Okay, so these are Fourier pairs. Now here the thing is, this is continuous in time. Okay, now we will discuss why I said continuous in time. Okay, so and then what we learned in week 7, okay, that aperture distribution is Fourier pair with whatever the intensity distribution you are getting. Okay, so intensity distribution you are getting, that these two are Fourier pair. Okay, but what you might have seen there, we had aperture like this, we had 2-point apertures like this, okay, or we had a aperture like this, something like this. Okay, but in reality we have a 2-dimensional aperture, means either it will be a circular, okay, let it be a parabolic dish, but however if you see from a top view it will appear as a circular. So with that the concept of 2D Fourier transform comes. So 2D Fourier transform is there already, similar to 1D Fourier transform, but here we will use 2D Fourier transform to see how the aperture distribution looks like in 2 dimension. In 1 dimension we already know, and we will already cover how the Fourier transforms looks like, but it's very interesting to know how the Fourier transform looks in 2 dimension. Okay, so now let's just skip a bit. Here also you can see this is CT naught or continuous FT, CFT, continuous Fourier transform. Now, and this is also CFT, continuous Fourier transform. Now what happens in continuous signals for between 2 points? Say I have a signal which is going from x0 to x1 or t0 to t1 or in any space. If it is in continuous Fourier transform, between two values there are infinite number of values, which cannot be stored in a computer or a computational device or a digital device. Okay, so for that we need to sample the signal which is coming, the analog signal. Now if we sample the analog signal and if we Fourier transform it, what we will get something called DTFT. Okay, discrete time Fourier transform. But what happens in this you will get a continuous Fourier spectrum. Okay, a continuous Fourier spectrum, again which you can't store in a PC, or you can't compute and show the result. So that's why what happens, we do sampling both in Fourier and time domain or the other space domain. Okay, so this is how a DFT equations looks like. Okay, now similar to this, 2D will be having one more term over here, e to the power minus say j k omega, instead of n that will be m and small m, and here will be double sigma. Okay, so this way 2-dimensional DFT will be there. Now a term which you will be frequently hearing is FFT. Okay, something called fast Fourier transform. Now if you see this equation, okay, if you remember clearly week 4 lecture 2, what you have a DFT matrix, then there is another matrix which is exponential matrix or this term matrix multiplied along with the signal matrix. Okay, now if you remember correctly, this is a matrix multiplication, which means this multiplied by this. So this will go into, if you program it, if you try to program it, just take it as a word, it will go into loop, means there will be multiple loops running to calculate this. To reduce that, an algorithm is used to reduce the time consumed for the calculating DFT, which is called fast Fourier transform. So fast Fourier transform is an algorithm which computes DFT or inverse DFT. Okay, so and there are multiple algorithms in this, but the collectively called FFT, which is nothing but a algorithm which can perform DFT. Okay, so here we will be using NumPy library, in which we will use this particular function, and also we will define our own DFT function by which we can calculate these things. Okay, so now let's take a look at correlation. What is correlation? There are two types of correlation: autocorrelation and cross correlation. So autocorrelation gives the how much a signal is correlated to itself, means like it will kind of give you signal power. Okay, if you remember correctly, it will be, as in Fourier domain, it will be x omega, okay, x conjugate f omega. It will be like this. Okay, so which is a signal power, and similarly here you will have a cross power between two separate signals. What is the power distribution, or how it is correlated to each other? Correlated means how it is similar to each other. Okay, now there is another thing called Wiener-Khinchin theorem, which suggests that if you want to save the computation time, what you can do, you can just use the take first signal, do a Fourier transform, then take another signal, do its Fourier transform, and conjugate it and multiply with each other. You will get the cross correlation. So cross correlation. Now, okay, so we will stop here and we will revisit the slides again for sampling concept. So let's see how we can visualize these things using Python. Okay. So if you log in, you will get this kind of notebook here. So you have to just connect it. So it will allot you, Google will allot you RAM and memory to work with. Okay, so what we will be using? We will be using two libraries here. One is called NumPy and another one is Matplotlib. Okay, so I will write here NumPy and Matplotlib and run it. You can, if you hold shift and press enter, it will run the code and take it to you to next line. Okay, so now what we will do, we will just we will have an example here of 1D Fourier transform. Okay, so I can delete this code and add a code here. So first we will define, as we said, we will use a user defined DFT function. Okay, here we will define a DFT function Now here, if you see 1D DFT function is n, which whatever the signal length we will give, okay, then n is we will define a length n, means a variable n for which the DFT function will iterate for or will go from one to another. And if you see this one, this is exponential matrix creation, and this is the DFT creation, which is E dot product of E and X. Okay, so this is what our DFT definition is. So we will just run this definition and go to next line. And what we will do, we will take few define few signals and add it together to see what is the frequency we are getting in it. Okay, so if we see here, what I have taken SR sample rate of 100, say we can say 100 hertz, then the time will be 1 by SR, the sample rate, or we can say it here Fs, okay, which is sampling frequency. We can say Fs is the best way to use it. So Fs, so now if we enter, and then we took few sine waves of different frequencies here. Okay, so in one the frequency is 1 hertz and second is 4 hertz and 7 hertz. So if we see how our curve looks like, it will be like this. See, okay, so so this command plt.figure sets the figure here of 8,6 size. Okay, so if you see the proportion is 8:6. Okay, now plt t means x, what I should plot in x, that should be t, and what we should plot in y, that is x1, which is the amplitude of the signal, added signal. Okay, so this is the shorthand notation to add into this. Means this thing means x1 equals to x1 plus this quantity here. Okay, so this means this. Now if I want to put a label, so here I am putting label. Then if I want to put label for your x, what I can do here, I can have say time and run it again. Okay, so here is this is the signal we have. Now what I will do, we will do a Fourier transform of it using the DFT function we defined, also using the fast Fourier transform function of NumPy library. Okay, so just we will write this code here. Okay, so here x1 using DFT function, it will call the DFT function, provide with the values whatever we are giving as x1, this x1 value. Okay, the signal, final signal which is created, we will give it into the DFT function, and the DFT function will calculate the DFT Fourier transform and provide it into x1, capital X1 variable. Now we will use the using FFT defined in NumPy library. Okay, so NumPy library we will use. So NumPy has a class called FFT, or the object called FFT, inside which there is a FFT function. Okay, so you don't need to understand this, but see, say NumPy is a very big library. In that there is a short library called FFT, and inside which you have actual FFT function. Okay, So you can understand it by like this. So inside which you can give your signal and it will calculate the FFT of it. Now this function, generally you can say the general format is np.fft.fft into signal comma number of points. Say you have a very large signal, but you have to calculate for first the FFT of first 100 samples. So you will give number of points there. So it will calculate the FFT for the first 100 samples. So we will also see that in the in upcoming examples. So here we will change this to FS. Now if you see here, if I run this, you will see what FFT spectrum. Okay, like this. Say you have near 1 hertz one signal, then positive side and negative side, and like sine wave have both side, na? But you see there is lots of means folding I have done here. Means folding means assigning different matrix like different way we have done here. Okay, so like the first half is the second half is the positive frequency and the third half is the negative frequency. The first half is the negative frequency. Okay, we have done kind of folding here and we use something called FFT shift to fold it. So what will happen if we don't do that? Okay, let's see in the next example. So we will have here, we will remove this FFT shift. Okay, now instead of that we will just have this frequency also, frequency. So this is just a means like this is just a x-axis. So we know that x-axis is frequency, so we won't bother about it much. So here it's error because there is nothing called function called t. So now see, now FFT spectrum is not like the ideal spectrum. Okay, or DFT spectrum is not like ideal spectrum. You have to fold it. Okay, you have to fold it to make it look like a real spectrum. So that's what FFT shift does. So here it starts from 0 to say some x value or the whatever the half of the frequency you are using, in half of the sampling frequency. Remember, half of the sampling frequency. And this also, this starts from say minus to here, that is there. So the first half is your real FFT and the second half you can ignore. Okay, so this is how the FFT is calculated. Okay, so now if we proceed further, let us take few more examples of 1D FFT, like standard functions. Okay, so let's take a simple sine wave and see what we will get. Okay, so let's take a simple sine wave here. So we have we will put here another label, x label, and then time and enter. So okay, so we have a sine wave, high frequency sine wave here. Okay, so now if we try to find out its FFT using our own function and as well as the function provided by the NumPy library, what we should expect the same thing whatever our function is calculating. So if you see here, see almost same amplitude and same thing what we expected. So if you take, if you remember clearly, in one of the examples in week 4, we said that the Fourier transform of rectangular function is a rectangular pulse is a sinc wave. Okay, but here you will see something interesting. Here you will see something interesting, which is pardon me. So it's saying there is no variable called x3. So this is not x3, this is x13. So here also it's saying x3, so it's x13. Okay. NumPy defined function. Okay. Now here, oh pardon me, so this will be x3 and this will also be x3. What I missed here is not calculating x3 using self-defined function and DFT of small x3. Sorry, this is x34. Okay. Now, yeah. So self-defined and this. If you see here, this is very interesting that this is not exactly a sinc wave. Okay. This is because the discrete Fourier transform is a complex number, and if you calculate the real absolute value, it won't show the sinc function. But stay tuned, kind of we will see in the 2D Fourier transform it's actually sinc. Okay, we will see there it's actually sinc. Okay, so let's take a few more examples. Like we already discussed that the Gaussian Fourier transform of Gaussian is always a Gaussian. Let's verify this. Is it true? Let's see. So here, as I said, we will use a different technique. We will say we will have 1024. We will compute for only first 1024 points. So we defined here x4, the signal. Okay. If we see here, the signal length. If we see the signal length here, len of x4, means len stands for length. Okay, so len of x4 is 80, but we are computing FFT in 1024 points. Now what will happen? Okay, so it will take that and it will extend the actual signal with zero padding on the both side. Okay, means kind of it will have a zeros on the both side and it will create this kind of graph. So here if you see the zeros is extended towards this thing, but the feature is Gaussian only. Okay, so let's move on to another type of function which is called sinc function. Let's see whether the sinc function results to rectangular or not. Okay, results to rectangular or not. So let's define a sinc function here. So if you define a sync function, and let's try to calculate the DFT. So what we are getting is nearly a square wave. Okay, square pulse, not wave, nearly a square pulse. So what is happening here is you have lots of you are discretizing in both time and frequency domain, which is making the system overestimate and underestimate at the edges. Okay, because of which this shoot up and shoot down and stabilization is coming here. Okay, so this thing can be tuned by having a factor, means a factor, time dependent factor, or some kind of slope factor into the sync. Adding the slope factor into the sync, you can have a proper square wave structure. But this kind of approximation happens. Okay, now if you trace the average line, it is just a rectangular pulse. Okay, and then let's see a few more example. We will take something called sawtooth wave. Means you have seen saw, right? So here we imported SciPy library, which is also a type of library in Python, in which there is a signal, a small library called signal. Okay, and using that we are calling a function called sawtooth function. See, it's looking like a saw, hacksaw. So that's why it's called sawtooth function. Means one side, right angle triangular wave, which is means like propagating. Now if we see this, if you can imagine it like a sine wave, also near to sine wave. So you can have it as a multiple sine wave, correct? You can imagine this as a multiple sine wave, correct? So you will think of as having one prominent sine wave and then gradually decreasing, means different harmonics of sine wave, right? So let's check whether it's true or not. So let's see here. See, it has a one prominent frequency and the harmonics started gradually decreasing, and if you add it up, it will make it a sawtooth in time domain. Okay, so remember Fourier series. Okay, now let's move on to the interesting example, which is 2D Fourier transform. Okay, so let's see. First, what we will take, we will have 2 point apertures a particular distance apart. Okay, so let's define a grid first. Okay, let's define a grid first. The grid will be, say we will have 512 cross 512. We will say 512 cross 512 meters. We have a grid. Okay, means have a area of 512 meter by 512 meter, where we will put screen or a screen, say, or you can say antenna or whatever sensor at say 200, 250, means in the center of the means this is row versus column. So row means your y-axis and columns means your x-axis. So your y-axis is 200 and your x-axis is 250, and the another one is at the center, which is 250 cross 250. Okay, near about the center, not the center because it's 512, so the center will be around 256. Okay, so we will initialize this parameter and we will create a inverse Fourier transform screen. Sorry. Okay. Okay. So what we have here, we have 2-point source which we are doing inverse Fourier transform. Okay, we have 2-point source, we are doing inverse Fourier transform to get the electric field distribution on the aperture, or we can say instead of doing IFFT we can do FFT also. Let's first see what we are getting. Okay, so now we are getting the inverse Fourier transform screen as a fringe pattern, means like fringe pattern, or the if you remember the Young's double slits experiment, you have bright and dark fringe. Say if I remove this I, we have FFT2. Okay, so what will happen? You will get the same, because inverse Fourier transform of 2-point source, or the Fourier transform of 2-point source, or 2-point source I am saying, or rather than source, 2-point aperture, in either do you inverse Fourier transform or Fourier transform, you will get this kind of pattern here. Okay, because those are Fourier pairs. Okay, if you are doing doing IFFT in one domain, you will get in another domain the fringe pattern type. Okay, so similarly what we will do, we will see if we have a thin wire screen. Okay, if we have a thin wire screen or thin wire aperture, what will happen? So we are defining a thin wire here, and let's see how the thin wire aperture looks like. So let's do an FFT over here, and after that let's write our plot routine. So one thing which I missed here is this. Here we are creating subplots, 2 plots, and we are using IM show. This is a type of plotting where you plot it as a as an image. Okay, so here if you can see here there is a thin wire, because of which we are getting this kind of diffraction pattern. Okay, now let's see if we have a rectangular aperture. This is the interesting thing which I wanted to show, because we discussed that this kind of aperture will result into sync wave. Okay, now if we have a rectangular aperture, so if we have a rectangular aperture, you will see a sync wave, right? You want to see a sync wave here. So see, if we have a rectangular aperture, what we are seeing, there is a gradual decrease in the pattern. So this is kind of sync. Okay, as the dimension increases or the time increases, the effect of the fringe decreases. Fringe, or say the intensity of the distribution decreases. The center intensity is the most. Now why it is like plus sign? Because it's not circular, it's a rectangular surface, so it has abrupt ending at two corners, so the diffraction pattern will be more towards the edge, not the corners. Okay, now if you see here, it is shifted by some function. It's not in the center, it's in the side of the screen. But if you remember clearly, if you shift a function in one domain, there is only one phase term multiplied with the Fourier transformed quantity, which is a constant value. So if you're plotting an absolute value, you won't be able to see that shift or the scaling factor. Okay, now let's move on to, say, if we have a circular pattern instead of circular aperture, or instead of a rectangular aperture. So what we should expect, we will see what we will expect, like a sinc function gradually decreasing over the area. So if you see here, see the sinc function gradually decreasing over the entire thing. But if you see clearly here, what you will see here is there is blobs. This is because this is not a perfect circle, because every grid is like a pixel. Pixel is a small box, means rectangle, square box. So that's why there is a blobbing nature is coming here due to the discretization of the screen. Okay, screen or say aperture. Okay, now if we have two circular aperture nearby separated apart, okay, two circular aperture with a separation, what will happen? Okay, this is interesting. Here we will step into the realm of interferometric principles. So if we have two circular aperture with separation say 50 meters, we will see some kind of resolution decrease. See, here we have resolution decrease. Say if I increase this to 50 to 100, so what we will see? See, we got more resolution, means the separation narrowed, means that if you see here, the first fringe or the first kind of lobe or the first distribution's width is narrower than the previous one. Okay, so if I reduce it to 10, what I will get a broader pattern than the previous one. See, here we have a broader pattern. Okay, because it almost collapsed with each other. Okay, so we have an elongated pattern because it became kind of an ellipse structure, so we have an elliptical pattern. So radius is 20, that's why. So if we have this as 20, just near around in the border, so we have kind of different pattern. So this is, say we have like a ring kind of aperture, then what will happen? So if we have a crazy aperture like a ring pattern, what we will see is the following. Okay, so here we will see the main beam at the center, whereas we have a different kind of harmonic ripples propagating out. Not different kind of harmonic ripples, but it has a different relation. If you see here, it is equally spaced. Every rings is equally spaced. Here it's not equally spaced. Okay, it's equal at a certain length, but there are two kind of rings which is propagating. Okay, inner and outer. Okay, now let's move to another topic, which is correlation. Okay, let's first define two signal. Okay, let us define two signals. One is say we will have one sinc signal, and one kind of rectangular pulse. So see, we have these two. Now what we will do, we will correlate this. We will correlate this. Okay, we will correlate this. So what we will get, for signal 1 we got the same signal as the sync but with an increased amplitude. Okay, whereas we got triangular for the first one, and if we combine both, we also we get a triangular only. Okay, because what is happening, you are getting the maximum value when the sync is in the center, and again gradually the value is decreasing. But if you see, the width is almost same, or this width is different than this width. Okay, there will be slight difference which you can't see with the naked eye. So let's do another thing. We will have a Fourier transform and see how the spectrum looks like. Okay, so here we will do FFT of both signal and the correlation of the both signal. What we will get, says for sync we got a rectangular pulse, for rectangular pulse we got a sync, absolute values of sync, and if we combine only, here it's RXX of signal 1 and here is RXX of signal 2. The table means like there is a mistake, so whatever it is. Now if you see here, you will see if we correlate signal by itself, the sixth signal we got a amplified sync, which also results in amplified rectangular pulse. And if you see we have a triangular wave here, we are getting kind of a triangular function or some kind of Gaussian or say decreasing sine, sum of sines. Okay, as we discussed for sawtooth. Okay, so now let's see what happens if we do something called filtering. Okay, so if you remember the concept from the heterodyning principle, what we do, we filter out the signal. But before that, let's just verify something called Wiener-Khinchin theorem. So here what we will see, Wiener-Khinchin theorem suggests that if you want to calculate the cross correlation, what you will have to do, you have to calculate the FFT of the first function and multiply it with the conjugate of the other function. If you do that, what you will have is this one. So if you see the both functions, both of them looks almost same. So there using Wiener-Khinchin theorem has lots of approximations involved or losses also there, but it's almost same and it's very computationally very fast. So this is that. Now let's understand something called filtering. Say we have multiple signals which is combined together. Okay, let's see, if we have say 3 signals, which one at 30 Hertz, which is 3 signals which has bandwidth of 30 Hertz and centered at for frequency 3 kilohertz, 5 kilohertz and 9 kilohertz. Okay, so here we will have few signals called FM, which has 30 hertz bandwidth. Okay, and we will generate 1, 2, 3 signal. Okay, and let's see, we have 3 message signals of message signal we are seeing is this is a message signal or some sort of signal. Okay, now what we will do in the real time, what happens, the signal is modulated, okay, is modulated at higher frequency. So say in heterodyne receiver, what we were discussing is we have something called H1 line, which is at 1.4 gigahertz, which we want to detect, but our systems work at much lower frequency than that. So what we do, we use a heterodyning principle multiplied by some signal and bring it down. So similarly, what we will do, we will multiply it by a higher value signal and we will create something called frequency modulated signal. Okay, so not amplitude modulated signal, by multiplying that to this. So what we are getting the final signal as this much. This is kind of garbage, you can't understand what is what. Okay, so what we will do, we want to separate out, say, the A2 signal out of it. So we will calculate a Fourier transform of it. So here you will see the essence why Fourier transform is so important. Okay, see here what you are getting distinct feature at points. Okay, means although it is so jumbled up, but you are getting this kind of distinct feature. Okay, now what we will do, we will create a filter at the center frequency of 5 so the 5 kilohertz band. Okay, so we will create a filter of say 50 plus minus 50 hertz. Okay, so since it's a very narrow filter, you will see like a square, but it's very short. So filtering is nothing but what you will do, you will multiply this by the Fourier spectrum we got earlier, which is this one. So if we multiply this, what we will get this. Okay, now if we do the inverse Fourier transform of this, we should get the actual signal. Okay, so what was the what we gave is this signal. What was the original signal at 5 kilohertz band is this, and what we recovered is the same. Okay, so you can recover the signal. This shows the importance of filtering. Now if we know the importance of filtering and Fourier transform, then there is something called sampling. Okay, then there is something called sampling and the loss factors related to that. Let's quickly go through what is sampling. Okay, so sampling is nothing but changing a continuous time signal, or that continuous space signal, or the continuous signal into discrete form by sampling at particular rate. Okay, at particular interval we will sample. So if you want to recover the signal intact, the sampling rate should be greater than 2 FM, where FM is your bandwidth, signal bandwidth you can say. Okay, so you have say a signal emitting at means having a bandwidth of 10 megahertz, so twice of that you should sample. Okay, why this? Because using heterodyne principle you can shift the frequency, center frequency. Say you have 10 megahertz across 1.42 gigahertz, but using heterodyne principle what you can do, you can shift this to say 0 to 50 megahertz. Okay, so then what you have to do, you have to sample with 100 megahertz, twice of this. How much, whatever your start limit and end limit is, with twice of that you need to keep your sampling frequency. Okay, we will see in a bit why it is so important. This is important because that will cause aliasing. What is aliasing? Okay, let's discuss this. This was discussed in week 4 also, but we will discuss a bit more about it. So if we have, say, a bandwidth signal which has a bandwidth of, say, minus omega, say 0 to 10 megahertz, 10M. Okay, now if you are sampling at the rate of what, say 50 megahertz, okay, what you will have a frequency spectrum in discrete Fourier transform. I am talking about discrete Fourier transform. Okay, so it will go like 0 to this. Okay, and here you will have this, and here to here. Okay, now say instead of 10 to this, we have 1 to something. So this will have, this won't be like this. This will be like here and here. Okay, now what will happen? What will happen if I decrease this to 20? It will be same. You will get same kind of pattern. Okay, but if you decrease it further, you will see a overlap in frequency. This is very difficult to understand in frequency domain. So what we will do, we will take it into time domain and see how and why this is important. There is something called oversampling. Oversampling means you have you have leftover band between two consecutive bands. Okay, so when you do oversampling, you have leftover remaining place here. Okay, which is not in use. So perfect sampling results in no space, but it is a thumb rule that you should leave some guard band over here. Okay, so such that if there is some kind of instrument error or drift, it won't go under undersampling and you have a signal loss. So it's like a kind of thumb rule that instead of, if you have a kind of bandwidth signal, then you should have the sampling frequency or at least three times the bandwidth. Fs should be 3 times the bandwidth, so that you will have 1 BW of guard band over here. So this will be a 1 BW of guard band over here. Okay, so this is what we use in we try to follow in radio astronomy. Now let's see what understand a bit more looking into time domain of it. So let's move on to our notebook. So let us first quickly again discuss what is aliasing means in time domain. Okay, now here by definition what we will have is, sampling theorem says that you should have more than twice of Fn. Okay, now this is why, because a continuous time signal, if we have a continuous time signal, okay, if we sample by the Nyquist rate, this is what also called Nyquist rate, we can recover the signal back. Okay, kind of more kind of intact at such that no information is lost. If this doesn't satisfy, what we will have some other frequencies coming, which is the signal will become indistinguishable. It's like we won't be able to distinguish like which signal it is, and therefore the information is lost. So let us see this example over here. So we have a signal at 2 kilohertz. Okay, this is a 2 kilohertz signal. Okay, going means we 2 kilohertz signal sampled at what frequency? Sampled at 18 kilohertz frequency. Okay, so we have 2 kilohertz signal sampled at 18 kilohertz frequency, so we will get this much amount of sample. Okay, so 2 kilohertz and 18 kilohertz frequency means in one cycle we will get around 9 samples. Okay, so 1 2 3 4 5 6 7 8 9, so in one cycle we have 9 samples. Okay, so 5 and 4 9, so one cycle 9 samples. So let's have another signal. Let's have another signal. Okay, which has a frequency of 10 kilohertz, but the sampling rate is same as the previous one. Okay, so what the sampling is happening at different frequencies, which you don't want. Means like, see, the sampling is like kind of haphazard. So what does this mean actually? If we see the plots here what is happening, the sampling rate is much lower than the Nyquist rate. Okay, so if we plot everything together, all the plots together, this is what we will see. See, this was a 2 kilohertz signal and this was the 10 kilohertz signal. If we sampled at Nyquist rate, we were able to recover almost the same signal. See, almost the same signal. There are some losses, but almost the same signal. But if we undersampled it, the signal is entirely lost. If we oversample it, no issue, you will get back the signal, but the extra bandwidth is utilized, which is not so good for the system, or it might means you might use your storage space, which is not required if you properly sample it. So this is what happens if you go under sampling. Okay, so with this I will say thank you.